The concluding talk of this day is a talk by, we're very lucky to have Professor P.P. Divakaran, who will speak about the history of combinatorics in India. And his talk will be preceded by a very short introduction of his colleague, younger colleague, Amri.
Thank you, Katerina. I just wanted to say a couple of words about Professor Divakaran. Professor Divakaran is a mathematical physicist, and he worked at the Tata Institute of Fundamental Research in Mumbai. For the last 20 years, he has been part of a small but dedicated group, relooking at a lot of ancient Indian texts in mathematics. And he has contributed in a big way to a better understanding of what is known as the Nila School of Mathematics from Kerala. He's also written an authoritative account of the history of Indian mathematics. It's a book published a couple of years ago called The Mathematics of India. And so I'll just hand it over to him now.
Thank you for having me, first of all. I have to apologize for the fact that a lot of the discussions in this apparently very stimulating conference are far above my head, so I have not been inside this hall very much. And thanks for turning up for my talk, which is going to be light relief after all the difficult stuff that you've been listening to. Now, the first question I would have liked to ask in a not so formal meeting is, how many people here have heard the name of Pingala? I would imagine not so many. I know, yeah, I've met two of them, and now I know that there are about a dozen. So I'm going to spend a little time explaining not so much who he was, because we don't know very much about him. I'm going to talk about the background in which he came to his interest, and he did what you people are here to celebrate, what it has become since then. Pingala himself lived approximately in the 2nd, 3rd century BCE, that is before the Common Era. And now it is more than 2,000 years, and the subject is flourishing. Witness this conference. Witness the Fields Medals this year. So it's wonderful. I'm very, very particularly pleased that I'm here. Good. So everybody can see what's on it now. Now, what I'm going to do now is, before I describe his own work, his own contribution to the founding of the subject of combinatorics, I'm going to give a little background about the history of mathematics before him in India. So you know in what setting he came to prominence. Now, there it is. Yeah. So things are clear. Now, the thing to remember is that in India, mathematics of some sort or the other has a very, very long history. It goes back to about 2600 BCE in what is called the mature phase of the Harappan or the Indus Valley civilization, which came to existence in the valley of the Indus River. I'll show you a map in a minute. The Indus Valley people left no records that we can read now. They had a language, presumably a very rudimentary language. We can't read it. Nobody can read it. So we have no account of what they did, except the artifacts that they left behind in enormous numbers, plus plus the seals and sealings on which their script is presented. And they have very interesting qualities. And the first thing is, what about their mathematical knowledge? They knew fairly large numbers because they had weights which went up to a few thousand of the fundamental weighing unit. If you take the smallest as a unit, the highest weight they had was about 3,200. So we know that they knew what to do to go from 1 up to 3,200. mostly multiplicatively, multiplication. So the second point says that in their artifacts, the binary ratio is very, very prominent. They had a very high level of technology. They produced very beautiful, very symmetrical bricks baked in a proper kiln. It's not just roughly made bricks dried in the sun. They were actually fired in very, scientists now tell us, in very highly well-controlled temperatures, the necessary temperatures. So they had high technology. These bricks are always in the edges of the bricks are in the proportion 1 to 2 to 4. So that is the first thing. Then their weights, which are extremely beautiful objects made from semi-precious stones, they also progress in steps of 2, 1, 2, 4, 8, 16, 32, then 1600, 3200, then 64, I forgot 64. So they progress both in a binary ratio as well as in a decimal ratio. So it's very difficult to know how they counted, if they had a base, what the base was. The choice is presumably between 8 and 10. And there are indications which say that 8 is more likely to be the base they used. That's one of the things they did. This depends on certain hypotheses, knowledge of languages and so on and so forth, so I'm not going to get into it. I'm quite convinced that 8 was the base. Then, these weights are doubled, I said, they are cubes. They are in the shape of cubes cut out of very fine stone. So they knew how to take an approximate cube root of 2, because that's how the weights progressed. Now, of course, everybody here probably knows, or most people will know, about the Delians going up to the Oracle of Delphi and asking, what do we do to get out of the situation of the plague that we are in? He said, make an altar which is exactly twice the volume of the altar that I'm already have. And of course, they did or they did not, I don't know. So actually the best part of the Indus is the number system as well as the geometry. Geometry is very interesting because, we're talking about before 2000 BCE. There is no evidence that they had the Pythagoras theorem. They had an understanding of it. There is nothing in the numerology of the artifacts which tells you that the Pythagorean triples were known, unlike in Mesopotamia, which came later. So I said these things, Mesopotamia, the old Babylonia, for example, the earliest artifacts, mathematical artifacts are about 2000 to 800 BCE. And till then, and that was the time when the Indus Valley civilization went into decline. But till then, they had extremely close contacts. We know plenty of things have been found. Our things have been found there, and their things have been found here. So it's a difficult problem to settle, but I'm sure it will be settled one day because there's a tremendous amount of work going on in this area. And they made very beautiful intersecting circles. They knew orthogonality coming from intersecting circles. They knew the theory very well, that the common chord intersects the said line of centers perpendicularly. And they used that to create extremely beautiful decorative patterns. And I don't know, Bangalore, the highway to the airport, there used to be lots of avenue trees planted on the left, especially in Yelahanka and beyond. And they had protective little grills made in concrete. And one of them used exact replica of one of the Indus Valley patterns. Yeah, and Indian fabric manufacturer, there is cottage industries people, they use decorative patterns which come all the way from 4,000 years ago. So it's a very, very, very strongly living tradition. So that is the first. Now, we don't know so much about them because now if you insist that I must have a text by which to substantiate what I say, then we have to start from about 1200 BCE. That is when a text called the Rigveda was written. Now, lots of people here, the Indian people who know about the Rig Veda will be very surprised that it figures in a talk on the mathematics, history of mathematics. The reason for that is that the Rig Veda is a religious text. It's a spiritual text. It's a text full of very visionary poetry. You know, it's a very beautiful stuff. But what is mathematics doing in it? The fact is that the Rig Veda has the names of about 2,000 numbers in it. A fact which is apparently went unnoticed for a very long time. And of these 2,000 numbers, many are complicated names, you know, not like 1, 2, up to 9, but things like 99,090, which you have to understand the principles of decimal number formation to make the name. So if you analyze the names, the arithmetical operations by which we make numbers from the base 10, such as multiplying powers of 10 by coefficients up to 9, then adding them up. All of them are now implemented grammatically because we have no writing. The real reason why people didn't pay any attention to the Vedic mathematical knowledge, arithmetical knowledge, is that there was no writing. No numbers were not written. They only had names. But names are as good a representation of numbers as written symbols are if you understand the principles. For example, that is how we read a polynomial. Nobody says 1, 2, 1. They always say x squared plus 2x plus 1. Okay. Even though algebra texts still say that a polynomial is a sequence, an infinite sequence of which all but a finite number vanish. I was very amused when I read that. That's the way the Indians thought later. Anyhow, that's a different story. So that keep this in mind, Rig Veda is a linguistic resource for understanding numbers and the total mastery of decimal numbers that they had. The Vedic people had no writing. So that's one reason why this knowledge was not considered serious knowledge. Because, you know, there was a tendency for historians to think that civilization began with writing. That is not true always, not only because oral history is a very, very powerful source of knowledge, also because in India there was no writing till about the beginning of the Common Era. Very little writing towards the end. But there was plenty of history, and we know that history. So, yeah. What is to be remembered from this slide is this last paragraph, in which I say that in nominal representation, that is giving numbers names, you don't need a zero. When you say 2022, there is no zero in it. You have 2000, 20, and 2 added together. So there was no zero in Indian arithmetic as a place value symbol till approximately the time of Pingala. That's one of the points I'm going to make. However, zero as a number, not as a placeholder, but as an integer, as the integer before 1, the cardinality of the empty set. That is a notion Pingala brought to light for the first time. This is not part of the combinatorics, but it's subsidiary to the combinatorics. It arises in a very, very interesting algorithm. Oh, this map doesn't come through very well on the projector. Now, I've said all these things. All of this happened in the northwest of India. Northwest of India, this is the river Indus. The various tributaries. This is the main river. And this area pretty much covers the extent of the Indus Valley civilization. It was a very extensive civilization, very large areas, large population. And the people we are going to talk about in the beginning, that is Pingala himself. Before that, the great grammarian Panini. And after that, a couple of other people. They all worked and lived and worked here, this area, which is called Gandhara in the Indian tradition. Now, these people worked Panini in 500 BC, roughly speaking, Pingala may be about 200 BCE. This was a time when very close contacts were established between India and nations and cultures to the west of India. For example, the great Persian emperor Cyrus, founder of the Achaemenid line, he conquered this area, most of this area. And Panini lived probably under his rule. Pingala himself is about 300 to 50 BCE. And remember that Alexander of Macedonia came and occupied this area for a brief time in about 350, I think, 4th century BCE. So this was an area of India which was very open to outside influences. And this was also an area which was a crossroads of the ancient civilizations of the time. So when people say that, we are nationalistic people, we accept nothing from outside. We only give, we don't take. That's a grave distortion of history, very grave distortion of history. Every time the Indian civilization has done well, it's been open to other civilizations. And I think it is true of all civilizations. That's my view. I had to say this. Now, why is it not coming? Oh, there. Yeah? Someone said something. No, this is... Now, this is important. This slide is very important. It's not about mathematics at all, except in a very indirect sense. Panini was the greatest grammarian of the time, and according to many Paninians, according to many modern grammarians and linguists, he was the greatest grammarian of all time. And enormous amounts of material have been written on it. Very, very, very detailed, very technical, very difficult to read, very difficult to understand. The commentaries are often more difficult to follow than his own text. His text is very difficult. I once tried and failed. But when you go through all these things and you summarize in your own mind what it is that was revolutionary about his grammar, it is this fact that he thought categorically. He did not, there is, as I say, he classified all linguistic objects into sets, what we'll now call sets. The Sanskrit word is better translated as categorized. The category is not in the modern sense of the term, but categories in the original linguistic sense. And then he set down rules not for individual objects in a category or not for any individual object. All the rules were categorical. All the rules were stated for all objects belonging to a certain set. And the sets are formed based on the commonality of their function, or in some cases, on similarities in the phonetic sense. That is, for example, there are certain rules of language which depend only on the phonology. It doesn't depend on the semantics at all. So when that happens, you classify all things. For example, all nouns ending in the vowel A will be one class. All nouns beginning with A, E will be another class. Then there will be a rule which says, how do you telescope them together? Instead of saying that, Nila and Utpala is Nila Utpala, what he will say is, the first category combined with the second category in that order, A plus E will become A. So, so this is really, set theory without axioms. That's what it is. And all grammatical operations, all linguistic operations were reduced to maps from sets, including maps within each set, that is a map on itself. Then immediately it follows, you can combine such maps. Okay, if the initial set and the final set of one map agrees with the initial set of the following, the preceding map, you can combine them together. So he reduced grammar to set maps and their compositions. Literally, there were exceptions because, this is a natural language he is dealing with, old Sanskrit. So when the exceptions come, he tell you, these are exceptions, be careful. So, so you would think that Indian mathematics will take off from this point, because, this is one of the using the structure of a set as defined by its, what you can do with it, is, for me, the most productive tool of modern mathematical thinking, including in physics these days. No, the Indian mathematicians had nothing to do with it. No, they didn't touch it. They never used categorization. Whereas our hero, Pingala, did. And for me, the true value of Pingala's work is not that he founded a systematic theory of combinatorics, but that he applied Paninian methods to a problem which was completely solvable. Okay, and Pingala's greatness lies in the fact that he did not, as earlier work, which sometimes are quoted as support for combinatorics, such as, for example, the Egyptian papyrus manuscripts. He was not dealing with individual puzzles. He was making a theory for a general theme. The theme is, how does one combine various objects which have different functions or which have different purposes? So it's a very, very categorical way of approaching a particular problem. The problem he was doing is, now, the book is called Chandas Sutra. It's a very difficult book to read because, since everything was oral, there was a tremendous demand on memory. And anything that was useful to enhance our memorizing power was taken over by the scientists, let me call them scientists, by the savant, by the people who made these subjects progress. And versification is a very effective tool of memory. It's a very powerful mnemonic device which lets you remember large quantities of things. Everybody remembers songs. They don't always remember prose passages. There were songs and things which have melody, things which have a structure, a rhythm. Those are easily remembered. So versification became very popular. So there was a problem. Can I have a theory of the means of versification we can have? That is the origin of Pingala's work. Now, what are meters? Now, before that, they have already done that. Yeah, the historical context, I should say. At about the time that Pingala lived, writing came back to India. Writing was present in the Indus Valley civilization, but nobody could read it. It disappeared completely. It's totally different from any language which came to India later. It is ideographic. It is written from right to left. It dispensed with many linguistic devices, so and it's unread. The writing which came in the middle of the 4th century BCE in India was very systematic. It's syllabic. The language is syllabic. The symbols represent syllables. It is not alphabetic. And Pingala, my feeling is that the reason why he decided to systematize the theory of versification is precisely because there was writing available and you could put everything down. I have no proof for it, but that's what I think. Now, during this period, many wonderful things happened. For example, mathematically speaking, they became extremely handy with negative numbers. Some negative numbers occur everywhere. In fact, they are metaphorically denoted as wealth as positive and debt as negative. And those are still the terms used in India for positive and negative. You say Rana Sankhya or a negative number, Dhana Sankhya or a positive number. All the texts use it. So that's already in the 3rd century text Arthashastra. So that is the other thing. Then numbers, very large numbers were, they realized very quickly that once you have the base 10, you can just go up in numbers without limit, no boundedness. You were not limited by a bound on the positive numbers. Result is that the word infinity doesn't occur in these texts, but there are any number of explorations of what it will be like if I then took the largest number I can think of and multiplied it by 10, what will happen? So many such speculations, and numbers were given names, and there are number names for things like 10 to the 55 in texts. And these are not mathematical texts. These are all texts which are basically, sometimes they are epic poetry. Ramayana and Mahabharata both have enormous numbers, of very large numbers. The Buddhist mythical writings also. So that is the background in which he lived. So what is a meter? Pingala made a theory of meters. And what's a meter? A meter is, first of all syllables in Sanskrit or most Indian languages can be said to belong to one of two disjoint subsets. One is called Laghu, L, La, and the other is called Guru, Ga, Ga. And Pingala himself named them, gave these sets names, and he indicated that one system, the short duration syllables are called L, the longer duration symbols are denoted by G for Guru. And I call them L and G, he called them La and Ga. I mean, he did it himself. I mean, it's not something which modern people have done. So a sequence, a line or a pada in a verse is a sequence of syllables, each of which belongs to one of the two subsets. So a meter is characterized by saying which sequence a certain line belongs to. That is to say, to every syllable, you attach the label L or G, depending on whether it's a short duration syllable or a long duration syllable. So these are now sequences, abstract sequences in two symbols called L and G. That's a line, that's a meter of a line. Now, a stanza can consist of 2, 3, 4, many lines. So when that happens, you have to say a sequence. You know, first line is this meter, second line is this sequence, second line is this sequence, third line is another sequence, and the whole thing is called a meter. But Pingala considers only one line meters. That is to say, how to characterize meters which are defined by one line, one pada. And of course, he classified them all, and most of them were of complete lack of interest to any poet. I mean, a very large number of meters can be constructed, and most of them were not interested in any of them. However, yeah, my feeling is that that was just an excuse. You know, what he really wanted to do was, what is the mathematics behind this? This has happened many times in India. You know, subsequently, mathematics was driven by astronomy in a big way, and a lot of people think that it is all astronomy. But there are lots of things also in the Indian mathematical writings in which astronomy is just an excuse, or sometimes not even an excuse. They simply say that, you know, I'm an astronomer, but solve for me Pell's equation. This is what Brahmagupta did. You know, these quadratic equation, Diophantine equation, it has absolutely no applications in astronomy. But Brahmagupta says it's very useful in astronomy, which is not. No, but the thing is, astronomy was a very glamorous subject at that time, because for several reasons, and not always very honorable. Because one of the reasons was that the charlatans decided that if they can predict the trajectory of a planet by looking at initial conditions, you can plot the trajectory of a human being by looking at the initial condition. That is, place of birth, time of birth, and so on and so forth. So astrology, horological astrology became extremely popular. So everybody pretended to be an astronomer. And so, you know, it's I've done. Yeah. So in this work called Chandas Sutra, there are 5 propositions. I use the word proposition because that's the nearest I can find to the word he himself used. The word he used, they're called pratyaya. A pratyaya is a statement which either is obvious or has to be proved. So I thought, you know, rather than say, or a construction to be followed, rather than get lost in terminological confusions, I will call them propositions because some of them are really propositions in the modern sense. Yeah, what are they? The first one is very straightforward. Find a canonical ordering that is given the sequence of L and G in a line, in a meter. Order them in some standard way. So there is no confusion, everybody follows the same order. And then second and third, given the ordering, if I tell you the index of a particular sequence in that ordering, what is the sequence of L and G? What is the meter that will come out of it? Okay. And the third is the opposite. That is, given the meter, what is its index in the list? The fourth is total number of meters of length n. The length is the number of syllables in a line, in a meter. So what is the total number of meters of a given, for a given length? And that's, of course, we all know the answers. All of them are very straightforward things. And fourth is, fourth I've done. Fifth is the one which this poster represents. That is, we'll say it's a statement about binomial coefficients, and the problem is, given a meter of length n, how many meters are there in which one of L or G is exactly k, when k is less than n? Okay. This is the one which everybody talks about, but actually, apart from the one, the others are quite interesting. Not because, none of them is very difficult. It's easy stuff. What is interesting is the way he answered these questions. That's fascinating. That's very modern. Yeah. The ordering. You can think of any number of ways of finding an order. What he himself did was, I have L and G, a meter of line length 1, first G, then L. Okay, that is the order for the length 1 meters. Then length 2, given any sequence, adjoin L and G, G and L in that order to the left of the sequence. Okay, so that's this canonical ordering. So this is unique. Once these rules are there, you cannot. There is a one-to-one correspondence between the index, which is in brackets, and the sequence, which is written out there. So to get all sequences of length n without duplication, all you have to do is adjoin G and L in that order to the sequence you already have in that order. So it's recursive. The way of doing it is assume that you already have solved the problem for n-1. To get from the solution to the problem with n, just add first G on the left, then L on the left. So with this, on the left. See G, L, there on the left, G, G, then L, G, then G, L, then L, L. Oh, you can do many things. I mean, you can do many things, the one he says, take the first in the previous sequence, first add G to it on the left, then to the same thing add L on the left, then take the next one. Okay, you figure it out. Now there are many ways of doing it. I'll do some other way in a moment. It's okay. Can I go on? Yeah. So this indexing is basic because everything is fixed on this ordering. Sometimes, I tell you, all devices these days are quantum devices, same input, different output. Point at the laptop. Oh, I'm the quantum guy, not the machine. Yeah. Now, the thing is, this is an interesting question because, there have been lots of people, the natural question, did Pingala know about binary numbers? Because that's what they look like, sort of roughly speaking. My answer is no, because, time is it? Oh, I don't have much time. Yeah. Okay, don't worry. Yeah, my answer is no, because, if you take the sequence as he has described them, you try to read them, give the value L equal to 0, G equal to 1, or the other way, you will not get binary numbers in order. It's easy to see. See, for example, if you take this, this is 0, 0. If you want to start this way, this is 0, 0. This is what? This is 1, 0. It should be 0, 1 in order. So we have to read it backwards. There are many ways of doing it. The one I'm going to describe is very trivial, but it's very good. So you have to read it backwards, or you have to do something else. You can redefine G and L and read the sequence backwards, or read the sequence right, but read the list backwards, but every sequence in the right way. Or, there are 3 variables. That is the value you assign to GLR to 2 choices. The order in which you read the set of sequences, either right to left or left to right, or the order in which you read each sequence, left to right or right to left. Take any 2 of them to work out. So the thing is, but he didn't know these things, because if he was doing binary numbers, why would he choose a decimal index? He wouldn't. The second thing is that, to say, binary numbers, you have to know that there is a 0. And there was no symbolic zero in India for another 700, 800 years. It came much later. So, but the thing is, if you were doing combinatorics of a 2-valued variable, sequences of 2-valued variables, what else will you do? This is natural. This is completely natural. The thing is, binary numbers are, all knowledge is now a string of zeros and ones. So it's very popular stuff. Yeah, that's better. Yeah. Now, yeah. Now, this binary count variant is very useful because if you have it, for example, the list as is given there, the way to associate a given meter to a given index is take the ith entry in the list. I want to know the index I, what is the meter that it represents? Take the ith entry, look at I minus 1, because you want to start from 0. Look at I minus 1, write it down in binary form. Then you will get a certain set of zeros and ones, a line of zeros and ones. Add enough zeros on the left so that the length is n. You make sure that the length is n. Then you associate L and G with 0 and 1 in the correct form. You get it. So, for example, there are these examples. Pingala's way is not Pingala's way. That's the point. What he says is, if I is odd, then you know that the first one is G, it begins with G. So I is odd, then your meter will begin with G. Okay. If I is odd, put down G. You already know that. Okay. And replace I by I plus 1 divided by 2. So what it does is to give you the one which comes to the right of this, the first entry. And if can carry on. If I is even, then put down L. That's because the second one is L. And then carry on. Keep on, you keep on doing it. Iterate till you come to the end of come to all n of them. So that's what I have illustrated here for n equal to 4 and I equal to 3. I equal to 3 means it's odd, so it's G. Then update I to I prime, which is 3 plus 1 divided by 2, which is 2. So you get L. Update it to I double prime, you get that, and so on and so forth. Okay. This is Pingala's way, by the way. It's not some modern historian who has done this. This is what he says you should do. No, 3 I have not described. It's just reverse the steps. It's so what's interesting here now is a method. The method, you've seen that now. It is everything that is done is recursive. It is as though repeating a step with minor changes, or repeating a step in which the next step will have as input the output of the previous step. Is the standard way of thinking in all these things. And that's not only in mathematics, it's visible in rituals, and even today in Indian music, Indian dance, Indian theater, classical theater like Kathakali, for example. It's full of iterations of various kinds. The literature, Panchatantra, stories within stories within stories. So this is very strongly a mindset which, according to the great scholars of India's past, like Fritz Stahl, who has been here several times, says that it actually has its origin in the rituals. Because in order to please the gods, you have to do certain things in a certain very precise way. And in order not to make mistakes, you repeated them so that one of them will be correct. And I think it's possibly true. I'm not very sure, but it's true. Now, the question arises, and not only is it recursive, almost all of them are descent methods. What you do is you take a problem and reduce the parameters which come in it in magnitude, bring it down till you reach the lowest possible level where it stops, or till you reach a level where you can solve the problem by inspection. So descent is Pingala's, the first use of descent consciously in Indian mathematics goes to Pingala. So he was what have I done? Yeah, he was a great guy. So the question then is, you can also ascend, you can go up, which is also very popular. And that also was finally done in India, much later in 1400 AD, 1400 CE. Formal inductive proofs, which one can actually translate the text and one will see. He'll tell you, do this, do this, do this. And he says, the astonishing thing is, the guy who first wrote about the inductive proofs, he precedes it by an axiom. It's very rare to find axiomatic statements in Indian mathematics, because everything should be obvious. Things which are not proved should be obvious. This is an axiom. The axiom is actually Peano's succession axiom. It says that the result of looking at the next number in this line of succession is the same as adding 1 to that number, to the predecessor number. That actually, when I first read it, it took my, I blew my top. I took my breath away. It's actually there in those terms, except then he says, he also introduces the notion of a predecessor. The predecessor of a number is what you get by removing 1 from the number that you have. So these are things which are not extremely well known. So it's not a bad thing to say these things. Yeah. Proposition 4 is about total number of meters of a given length, or length n. And of course, we know the answer is 2 power n. Pingala knew the answer too. Why? Because he knew that when you go from length n to length n plus 1, you have 2 options, add an L or add a G, uniquely, in a unique way. So every step multiplies the number of meters by 2. So if you take n steps, of course, you get 2 power n. But that's not what he does. What he says is, if what he says is, replace n by n of half n whole squared. That is, and this, if it's 2 power n, this is the correct thing to do. I mean, it's a true statement. But he didn't know it was 2 power n. He says his recipe is take n of n. You want to find n of n, okay? And you know, yeah, you replace it by n by 2, the number of meters of length n by 2 whole square if n is even, or remove 1, write twice. You take 1, 2 out, you will be left with an even number. Take half of that, take the square, then iterate. Okay? So rather than explain all these things, two examples, n8, for example, according to him, is n4 squared, descent again, n2 to the 4th power, n1 to the 8th power, 1 of length 1, there are 2 meters, so it's 2 power 8. If n of 7 is twice n of 3 squared, because I've taken 1, 2 out, then I've taken 7 plus 2, 7 minus 1 divided by 2, which is 3 squared. 3 is odd, carry on. So you get 2 power, 1 plus 2 plus 4. It's easy to check. So why did he do this fancy factorization? Nobody has an answer to this question. I mean, many historians have written about this, and I don't know what the answer is. It's very, very curious fact. People say, modern people who know, who are literate in computer mathematics, they tell me that, oh, it's because the number of multiplicative steps is reduced, which is true, but the numbers get bigger. How do you get to the big numbers? By doing more multiplications earlier. So I don't know what the answer is, but this is what he does. I don't know the answer. Yeah, take 10 minutes. So as you can see, I have spent a lot of time on Pingala because, his thinking runs through all work on combinatorics in India later. Everything is recursive. Everything is, a lot of Indian mathematics is descent mathematics. It actually takes, for example, the solution of Diophantine equations. It's always done by reducing the coefficients. So it's quite remarkable fact. Yeah. So how did the 0 come into this? In these intermediate steps, I said, if it is even, do this. If it is odd, do something else. So he says, call whenever you get an even number as the nth step, say that it belongs to a set. When you get an odd number, say that it belongs to another set. And these sets are given names. The names are 2 and 0, Dvi and Shunya. Shunya is the word used. And Shunya, meaning void, cannot but be 0, because Dvi has only one meaning in Sanskrit, which is 2. So this is the first inkling we have that the number 0 was understood. This is not in a place value context. It is a number 2, number 0, like 2 is a number. So, it's a remarkable man. He must have done. Yeah. Or whenever you see a star on some words, what it means is that they are of Indo-European descent, and you can see Dvi is 2, which is the same in many European modern languages, and also in old languages. And I have also done this for things like pada, foot. They are the same word. Proto-Indo-European, they are the same word. This is very easy. This works very well. Binomial coefficients is my last proposition 5. Now here, there's been a fair amount of writing on the subject. And I have said somewhere earlier that the person who really made sense of what Pingala says by reading a verse which was not read by other people and by using the commentary of other people who came later is that this is done also by descent, but in a very unusual way. First of all, that there is a symmetry. K K is the number of syllables, number of matras, the number of syllables which are either L or G, doesn't matter. So there is a symmetry. The K is fixed. N is the length of the meter. The question is, how many meters are there in which of length N with K fixed? And we know the answer is the binomial coefficient Nk. But what he says is, to get all meters of length N with K fixed, without duplication, do exactly what we have done before. Adjoin L to every meter which has K minus 1 Ls. So the number of Ls now gets updated to K. And adjoin G to every meter of length N minus 1, but K unchanged, because this G doesn't change the number of Ls, just increases the length. Okay. So what does that do? It gives you a recursion relation. Gives you the recursion relation which says Nk is N of N minus 1 length and K minus 1 Ls plus N of length N minus 1 and K Ls. So this is the recursion relation. You want to solve this. That's Pingala's problem. And what he does is, of course, not surprisingly, descent. Well, we know now that this is exactly the binomial coefficient recursion relation. So we won't do any work. We'll say, oh, I have got the binomial coefficients. But Pingala's solution is, take the second term, this term. You see here, we have reduced K by 1. Here K is the same. Now apply the same recursion relation to this term, which means N minus 1K will replace N and K, and this will become N minus 2 K minus 1, and then there will be an extra term which is N minus 2K. That's what you'll get. Repeat. This is what you'll get. At a certain point, it will terminate because K must be equal to N maximum. It cannot be more than N, because there cannot be more Ls than the total length. The result is that it terminates. So you have a iterated recursion relation. Now apply the same recursion to each of these terms. Okay, so you'll reduce the K a little by N, and you will reduce K little by little till N minus the N and K. N will become less than the K in each of them. Okay, stop there, add them. Okay, he doesn't give you the answer, he tells you what to do. And presumably what he does, according to Jan Shah's name I mentioned in one of the slides, that's very good reading, by the way. He's terrific, excellent piece of work. So when you do that, what you find is that you can plot this as you can plot the ends as points in the nk plane. You start with n equal to 2, k equal to 1, which is equal to 2, by the way. And then you plot it, and what you get is what this picture tries to say. This is the Suji Prastara. Okay, you get actually a variant of the Pascal triangle. And this was done not by Pingala. The graphical representation is not due to Pingala, it is due to another combinatorial guy, performance arts combinatorial guy, I should say, named Halayudha, who lived much later, who lived in the 13th century. So, of course, Pascal did it too, somewhat later. Now I'm going to skip this very large, not very large, a fair number of very, very brilliant people who contributed to combinatorial mathematics in India in a very systematic and productive way. I just mentioned the names. Bharata, who is the person who wrote the Natya Shastra, who's a text which is still in use in India in the performing arts, in dance and drama and music. Virahanka is a very remarkable guy. I'll come to that in a minute, so I will skip that. Halaitha I just mentioned, he's the one who plotted the first Pascal triangle. Sharangadeva wrote a book called Sangeeta Ratna. Yeah, now I'm back normal. Sangeeta Ratnakara, Ocean of Music, which is an extraordinarily rich book and extremely complicated combinatorics, because now we're dealing with music, and music has 7 notes and 4 tempi, 4 matras. And so you have to, you get fairly complicated, hairy stuff. And it's all worked out. And the real breakthrough due to Sharangadeva is that he not only did the Pingala stuff, that's the kind of things that straightforward combinatorial stuff that I already described, but in this larger context, he also did things like finding generating functions for these coefficients. You get all kinds of wonderful numbers, sequences of numbers. For each of them, find a generating function. So like the binomial series, the binomial series, the coefficients come by expanding 1 plus x power n. So that's the kind of thing that was done. And for this, there is an absolutely magnificent review by our good friends, Raja Sridharan, R. Sridharan, and M.D. Srinivas. Very, very good. And it's very easy to get because it's in the CMI History of Mathematics seminar volume, edited by Sheshadri. And finally, I will mention Narayana Pandita, because he was another of the people who have been ignored by historians for a long time. Even though his name is known, nobody has given him credit. He did everything. He did geometry, he did algebra, he did number theory, he did magic squares, he did combinatorics, and all of them at a very high level, one of the greats. One of the greats of Indian mathematics. So I do some technology is not easy to master, I have to say. Very quick. One of the things that Virahanka did was, in music, very critical is the length of a cycle in time, the duration of a cycle in time, because there is the rhythm guy, the guy who beats the drums, and he has to have a pattern to follow, and which is strictly cyclic. And the singer has to fit his performance into that. And the singers, both of them can combine various tempi, long, short. I mean, like, for example, in the traditional Indian way, there are 4 tempi. There is Dhruta, Laghu, Guru, and Pluta. 1, 2, 4, 6. And all Indian talas are based on this counting, with some exceptions. And so they have to match. So duration. So question is, the first part of, the thing is, a guru lasts twice as long as a laghu lasts. So the question is, what is the time duration? For a given time duration, how many talas are there? How many rhythms are there? And the problem is not very, it's actually simpler than some of the earlier Pingala things, because what you do exactly the same thing. To get to duration n from n-1, you can add a g to n-2 because it is twice as long. Or you can add an L to n-1. So you get this recursion. I mean, that is the Fibonacci numbers. So this is, and here again, I have given a reference to Parmanand Singh, the wonderful little article, not very little, very nice article on the complexities that you can build on this basis. And Parmanand Singh is, I think, no longer alive. He's a very distinguished man. He's done very fine work. Not very well known, unfortunately. Those who want to read more, I can. You don't have to note down anything. I can give you the references later. A change of scene now. I want to now give a hint of how very, very beautiful advanced mathematics that a man called Madhava did in the 14th century, the end of the 14th century. And what he did was actually to invent calculus. That sounds like a very irrational claim, but it is strictly true, speaking true. How many people here have heard the name of Madhava? Oh, that's much better. If I'd asked this question 10 years ago, not a single hand would have risen. Yeah, he was one of the titans of mathematics, not only Indian mathematics. He actually did calculus for trigonometric functions in a way which is much sounder than Newton's. It's very similar to Leibniz's approach to calculus, not Newton's. Newton is very, Newton is a very focused person. He knows where he wants to get. He'll get there by hook or by crook. So, for example, he himself will say, I shall do this by analogy. Actually, he has actually written this. So, extrapolation and analogy. Now, Madhava's work is on calculus. One of the things he is well known for now is the development of the sine series, the power series for the sine function. He did it. What he actually did, I'll come to in a minute. But the method is very simple. You want to compute something which is a non-linear function of the variable. You linearize it locally. You cut it up into divided by n. For example, rectification problem, take the length of the arc, divide it by n, and do all your calculations as though the arc is a straight line at each point locally, and then add them up and take the limit n going to infinity. Okay. No philosophical confusions about what is meant by an infinitesimal, no such things. So, Madhava did this for several things, it's really beautiful stuff. And then, for example, recursion, the power of recursion. How did he find the power series for the sine? In modern language today, with infinitesimal calculus familiar to all of us, this is what he did. He set up the differential equation satisfied by sine, turned this into an integral equation. And this is the integral equation. This. What you do now is you have sine z here. Substitute for sine z this expression, the whole expression, because that is what sine x is. So you get a series of terms with multiple integrals. And the first term will be, in the first term, what will there be? This x will be, in the first term in this will be another x. So you'll get x squared integrated, you get x cubed divided by x squared. X squared divided by 2 integrated again, you get x cubed divided by factorial 3. So that's what he did. It's very elegant. Now, how many of us have done the sine series in that way? Very few, I'm sure. Then, what he actually did was doing all this not by taking the limit, but before taking the limit. Then you get this hairy equation. This equation. This is an equation for sine x in powers of sine x divided by n, or x divided by 2n. Depending, you can choose any n you want. This is a generalization of the formula. Sine theta is 2 sine theta cosine theta for general division. And it's very difficult, it's very hairy stuff to get there. The coefficients are not explicitly given. Coefficients are shown to satisfy this recursion relation. You see, the coefficients they increase. As this index increases, the n decreases, and coefficients are defined by sk of n is the previous such sum.
I'm sorry, Professor Divakaran.
Previous such sum, but indexed by I and summed over I from all the way.
I'm sorry, could you please finish in 5 minutes, something like this?
I will finish in 3 minutes.
3 minutes, okay, perfect.
Finish in 3 minutes. No, this is very beautiful stuff, So so you do that, and when you do that, you get these things satisfy the recursion relation, is kn, is k minus. This is what you get. You separate one term and you do all these things. And finally, what you find is that this equation has a solution, which is also a binomial coefficient. And it satisfies the recursion relation is the same as Pingala's recursion relation. So, so it comes in all kinds of unexpected places. Yeah, this I don't have to say. This is just this is vague generalities. Yeah, that's it. 3 minutes, I said 3 minutes.
Thank you for your.
I thought I had it. I thought I had my talk under control. 1 hour. No, it took a little longer. Yeah.
Are there any questions or comments for the talk?
Oh, you have. I know now. Dinner is weighing on everybody's mind. Yeah, you know. Yeah.
You have spoken about the pioneers of
Yeah.
combinatorics in India.
Yeah.
Could you say a little bit about dissemination to what? How did they disseminate the work? How widely was the work known?
Very difficult question to answer, you know, because as I said, all these people worked in an area in which there was a tremendous amount of traffic. You know, there were many Greeks because this was part of Alexander's Indian Empire. Seleucus was the governor. And there were very close contacts during the 2nd, 3rd century BC between Northwest India and Alexandria, for example. Okay, but we have no evidence. We have really no evidence. In fact, I have often felt that the only evidence we can look for is mathematical commonalities, because historically there is no evidence. Yeah. What about things which flow into India? In the other fields, we know that there's plenty of borrowings, like, for example, architecture. Many features of Indian temple architecture, Buddhist architecture, are borrowed from classical Greece. That's well known. Also in sculpture, you know, certainly it's in that style was even called Indo-Greek at one time, because, you know, it is this influence of the Athenian and the Alexandrian sculptural tradition is very strongly visible in Gandharan sculpture.
I'm sorry, actually, I was referring to the work that Pingala did within the community that he lived in. Do we have any idea about, you know, was he working in isolation, like
No.
schools, or whether?
No, we have no
disciples?
no knowledge of him as a person at all, none, nor about the society in which he lived. Okay, we really don't know. We don't even know exactly where he lived. There is about, for Panini, we have some information. All we know is that he was from that area. And that was a hotspot of cultural exchanges at that time. That we do know. We cannot be more specific. Yeah. And there's a lot of work to be done, you know. Yeah.
I have quite a few questions, actually.
Oh.
So, yeah, I know. So firstly, when Pingala was calculating 2 power n, he gave this algorithm in terms of going to n by 2 or n minus 1 by 2.
Yeah.
Did
Yeah.
he justify that? Because, I mean, to us, 2 power n
No.
is obvious.
He justified nothing at all.
I see.
You know, his sutra style, it cannot be read by ordinary people. It can only be read by people who have deeply absorbed his way of thinking over many generations. So it is not for nothing that the commentators are always a few hundred years later. It takes time. And reading, I mean, Panini, for example, I mean, I have friends, very, very fine scholars of grammar, who say that we understand Panini much better than, let us say, Bhartrhari did, who was a great grammarian himself, who lived in the 5th century. Time, you know, these are very compressed aphorisms, and it's very, very difficult to pierce into their ways of thinking. So that's one reason I think, like, I mean, you haven't, give me another minute. I give an example of something which I know from my own experience, my own work. There are passages in Aryabhata's great work on mathematics and astronomy in which he uses the word Brahma. Okay, for a very long time, people thought that it referred to the god Brahma, which in Sanskrit is a masculine gender word. In our work, we came to the conclusion that it doesn't make any sense for it to be Brahma. So, but if you look at the declensions of the words which follow, or Brahma itself, you realize that this Brahma in Aryabhata is not masculine, but neuter gender. So it referred not to the God, the creator, it referred to the Brahman, Shankaracharya is Brahman, the pervading spirit that runs the universe, which is not a personalized God. This, it had to wait till 2020. It makes no sense, no, but this happens. Happens all the time.
Okay, my next question is, so Pingala defined the even and odd numbers and he referred to them as Dvi and Shunya.
Yeah.
Wouldn't it have made more sense to refer to the odd numbers with, say, Eka, which is 1? 1 is actually odd.
I don't know. Yeah, that occurred to me too. Why didn't he say 0 and 1,
Right.
for example, or 2 and 1? Yeah, I don't know. I don't know the answer.
So, is this the first time the word shunya appears in any text?
This is the first time the word shunya appears in the sense of being 0. Yeah, shunya as emptiness or void was known before. But in grammar, there is a situation in which there are certain things which disappear, which are not there, leave an empty space behind. Shunya is not used for that normally. Normally, it's the word uses lopa, lacking in something. Yeah, but as a number, this is the first time. As far as I know, subject to correction. Who? No, Panini doesn't use the word shunya, he uses lopa. Yeah. And that's well understood. He's from Kerala, so you will know something of the Sanskrit grammar. There is a samas called Madhyama Pada Lopa, which is, there is a middle word. When you bring them together, you drop it without changing the meaning. And it happens all the time. It's in Sanskrit grammar. So lopa is used in that, many examples are given. It's not replaced by a symbol which says 0, by the way. Well, I should have taken less time.
So, just a comment on this. So he's really, the shunya comes as 2 raised to the power 0 equal to 1. And then dvi is 2 raised to the power 2. Because he's describing 2 raised per something, right?
Anything raised to the power 0 is 1, so why 2?
No, so he's in your algorithm, he's calculating 2 raised to the power n, and he's reducing it down. So these are the last 2. So it makes sense to say shunya is 2 raised per 0. Huh? No, 2 raised per 0 and 2 raised per 1. So so I'm just
saying, the exponentiation, 2 power n, you will not find in Pingala or anywhere else. The Indian arithmetic people had 4 major operations, the usual ones, plus 2 other operations, square and square root, which were considered fundamental operations. But exponentiation was not considered a fundamental operation, because if you did, you would not need new names for powers of 10. You would simply say 10 power 2 for 100. That is not the case. You say shata. You don't say dvidasha, for example. You don't say that. So exponential functions were not considered seriously in India. Yeah.
I think that Professor Divakaran is invited to the banquet. Yes. And so,
what? Sorry again. What? Oh.
So you have a very popular talk, and you have plenty.
Thank you very much. I'm a very tired man, so we'll see. Thank you. Thanks all of you.